Hello and welcome to my channel. In this video I'll be talking about some generalities of the project you saw in the previous video, like hardware setup, program size, execution time, and so on and so forth. So without further ado, let's begin. Okay, so first let's talk about the hardware I used, the virtual hardware I used to control this whole plant. So let's open up the devices and networks. And as we can see, I have a 1200 series PLC, a 1217C to be more precise. And I chose this PLC because I have only the basic license here on my whole computer. And this also means that the 1500 series PLCs are simply not available to me, so I had to stick with these. Also, I was actually quite curious if this kind of PLC can handle a large plant like that, so I stuck with it. Okay? Of course, I needed some extra hardware to be able to control the entirety of the plant, and for that I chose a ET200AL based distributed I/O system. And the reason I chose this is because I wanted something that is fast and very much decentralized. If we open one of these up, we will see that this distributed I/O system is actually composed of individual and separately mounted I/O modules, which is very similar to an ASI system. In a plant like this, where we have lots of devices but the I/O signals are quite spread out, such a system would actually be, in my opinion, a better tool that we can use. Okay, so let's move on. Okay, so the next topic we can discuss is the program size. So let's open it up. And what we see here is that the PLC is able to house a program of 4 megabytes in size, but our actual program is just over 2 megabytes. And I think it's pretty neat because if we think back how many devices we are controlling, then a program size of about 2 megabytes is actually quite slim, in my opinion. And if we check out the work memory requirement, is just about 100 kilobytes, a little bit above 100 kilobytes. So this is the amount of RAM we need to run all that. So I think it's pretty neat. Of course, the other interesting question is how quickly can a program execute on this 1200 series PLC? Well, I won't start it up now, but the cycle time is about 100 milliseconds, which is, in my opinion, horrendously long. But these PLCs are not high-end PLCs. So in a real-world project, you would probably want to choose a 1500 series PLCs, or you might want to be able to divide this program up and distribute it to several individual PLCs. Also, if we think about all this a bit, then we will also find out that it's not so easy to exhaust the amount of memory it provides you. Okay, let's move on. In this small section, I will be discussing this quite ugly and small HMI program I created, the main purpose of which is to commission and test the program and the plant, and that's about it. So it's very minimalistic, and I didn't really do much about the aesthetics either. So really it served its purpose, but I'll show you because why not, okay? So this is the root screen. Here we see the global plant control. With these buttons we can start, pause or reset all the devices in the plant, so we don't have to click them one by one, which is great because if we want to start up the plant, then we can do it with a single button. And these two are controlling the two emitters we have. So one of them are controlling the box emitter, which puts the boxes on the belt at the very beginning of the plant, and this one puts pellets right before the pelletizer machine. Okay, the next screen. This is basically the first screen of the aerial view of the plant. So with these buttons in the bottom left corner, we can navigate through the entire plant. So if we go up and down and left and right, we can see that we have different sections of the plant. And these are the CNC machines, for example. And we can view all the items that are being conveyed. And in case of the pallet section, the item IDs as well. And we can see if the conveyors are moving back and forth. The next screen, here I can control the individual devices, but since the PLC is not running at the moment, it doesn't work. It relies on the PLC because in the basic panels, you cannot dynamically change the text list of these drop-down boxes. So I needed to create a screen for each device type. This is for the CNC machine. When I would select a device here, the PLC program would detect which one I selected, and it would switch to an alternate screen which looks quite identical to this, but the boxes would have different text lists assigned to them. It's a trick I use to be able to control different devices, but I know it's not an ideal solution because in real projects I really like to keep HMI programming and PLC programming as separate as possible. And here we have a very clear interdependency. So the HMI really depends on the PLC program running, which solution I think is actually pretty bad. But this is the limitation of the basic panel, so I had to overcome it somehow. Okay. The next two buttons here are basically showing the two racks I have. And from these screens, one can open up the fetch screen where one can type in the ID that is stored in the rack, and we can manage the retrieval queue here. That's about it. That's all the HMI screen supports right now. For the needs I created it was enough. Okay, so let's move on, which will be the scripting. This is basically a feature I already talked about in the overview video, where you saw that, for example, a 3D robot could perform different tasks even though the control block is exactly the same for both of them. So one of them was picking up pieces from the same position and laying them out onto the same conveyor, while the other was able to pick up pieces from very different position and then lay them out and assemble them at another conveyor. So how did I do it? Let's check it out. So if we open up the sequences here, then we can see that we have quite a few arrays here for each device that uses scripting in the plant you saw, and each array actually hold a sequence of stages or actions. I call them stages, but they are actually actions. And in the control block, if I open one of those up, oops, they are not here. They are in the devices. Let's open up this one. So what we see here is that, for example, the grabber control has the logic that controls the grabber. We can turn on and off. So if we open this up, that we can see that we have a stage for turning it on, and then we have a stage for turning it off. And the way I did it is, once you call such an action, program will detect if it finished, and once it finished, you can execute a next one. What is actually responsible for it? This control block can not only execute stages one by one with the manual controls, but as we can see, we have a stage sequence here. If we provide an array containing these sequences, then it will go through each and every one of them. So basically it's like scripting. You're giving the control blocks commands one after the other. So this is not a state machine because it doesn't make any decisions based on any sort of information. It just executes each stage one after the other. And how such a sequence looks like. For example, if we open up for the unstacker, then we can see that it really is just a list of numbers. This is all it takes to lay out all the 5 pieces to the conveyor. It's that simple. And obviously, if you would change this sequence of numbers, the device would do something very different. Of course, it's not enough to provide a sequence of commands to the control block, but the crane also requires coordinates to which to move, and this is basically here. So we have 3-dimensional points here, and this is what it goes through. So this is about it. Okay, I think that's enough for this video. Thanks for watching. See you next time.